So in the last lecture, we started with understanding the numerical methods for this initial value problem, which consists of this differential equation together with this initial condition. Right, so let's call this 1 and this is 2. So the first method in this direction we obtained is the Euler's method. And what is this method? How do we find? So basically, whenever we are talking about the numerical method, so we will have a underlying partition of the domain. So let's call this is at x0, x1, and let's call this is at xn. So x is in AB here. Okay, where A is x0. So say we are interested in finding the approximate value of the y at the endpoint, at the B. Okay, so we have the partition of the domain, which is an interval here, into these subintervals. And we consider all these subintervals, they have an equal length. That is, we consider any of the xj, it is going to be x0 plus jh, where j is varying from 0 up to n. Okay. So how do we obtain the approximate solution of y at any node xk, which we denote by the yk? Okay, so we found it at yk plus 1. That is the approximate solution at the node xk plus 1. This is going to satisfy that we can obtain this by this formula. Okay, so if you try to focus on the given differential equation, this at any point x, y prime is given by f of x comma y, right? So this means that y prime is nothing but denoting the slope of the solution curve y at the point x, right? So which is the same as the f. So f basically denotes the slope here. Okay, so you can observe here that we obtain the, so you have the approximate value of the solution at the previous node xk, and you use that to obtain the approximate value of the solution at the node xk plus 1. Okay, and then we also saw the concept of the truncation error. That is a truncation error for this method in particular. And how do we understand the truncation error? So if you observe that this is for a given method, which is this method in our case. So if you try to see the correspondingly, if I mimic the same behavior with the exact solution, that is here I have yk plus 1, which is nothing but the approximation of the solution y at xk plus 1. So if I consider y at xk plus 1, right? And then here I have yk. So if I consider at y at xk, and then here I have this term. So correspondingly, if I consider xk and y at xk, so the question is that observation is that you're not going to have equality here. Okay, so y at xk plus 1 is not going to be equality here. This is, of course, is going to be an approximation. So there's some error present in this this approximation, right? So if I want to write here equality, so you can observe that we obtain this term h squared by 2 y double prime of jk, right? So with this term sitting here, we have the equality here. Okay, that is a y xk plus 1 is the same as this term. So what is a truncation error? Truncation error is basically if I try to mimic the method using the exact solution, that is if I take this, I know that this is not 0, right? In the case of the exact, when you have approximate solution, you have that yk plus 1 equals this thing, right? But y at xk plus 1 is not going to equal this thing, right? So this error which we get, this we denoted by the truncation error, and I think we denoted it by tk plus 1. Okay, so this error is called truncation error, and we can simply observe from here that this is nothing but this term, and it justifies the name also, the truncation, right? So basically we are truncating it. This we obtain by truncating the Taylor series, so which is h square by 2 y double prime of ji k, where this ji k lies between xk and xk plus 1. All right, and then we also saw that the total error, that is, we have the approximate value of the y at xk, y k, right? So this error, which we denoted by ek, so under certain assumptions, we obtain that this is less than equal to some constant times xk minus x naught into h. All right. So if we try to see, finally, we will be reaching to the last step, right? So if we try to see what happens for the k is equal to n, so basically En, this is going to be less than equal to some constant times. So this constant is not depending on h here. Okay, so this will be mod xn minus x naught into h. So this xn minus x naught is nothing but the length of this interval, so which is b minus a. So basically what we have got, that the error behaves like h. Okay, because this is a constant, both does not depend on h. Okay, so the two observations from here, that the truncation error is behaving like h square. Okay, but the global error, this behaves like h. Okay, so you can treat the truncation error as, so this is a remark. So truncation error, this is which is a local error basically. This converges with rate h square, which you can observe from this equation. So if I give it as 4 and this as 5, which you can observe from equation number 4. But the global error, this converges with rate h, which you can observe from equation 5. Okay, so basically you can treat that global error is nothing but this is the sum of local errors which are accumulated over all the steps, right? So in a way, I can see that my global error is going to be local error, and then how many steps we have? We are having n steps, right? So this is the number of steps. Let me write it. Okay, and local error we have already seen, it behaves like h square, so it is going to be some constant times h square, and the number of steps we have is n. So, and we know that n times h is nothing but the length of the interval, which is b minus a. So basically what we get is a c of, let me write in terms of xn and x0, xn minus x naught into h. So which is basically like behaving like h. Okay. So when we are going to see the further methods, so whenever we have to design a method of, say, order h raised to power k plus 1, that is, if we want to have the global error of this order, it suffices to design a method which will have a truncation error of 1 higher. That is, if you design a method which will have a truncation error of order h raised to power k plus 2, eventually the global error will have the order h raised to power k plus 1. So you will lose 1 power of the h when you will go to the global error. Okay, so it suffices to check the truncation error, that what is the order of the truncation error, and when you are trying to derive the global error, you will lose 1 power of the h with the similar arguments. All right, so here you can see that if you try to see the error for the Euler's method, if you reduce the met size by half, that is, here you have the length of the intervals are h. Each of the interval, sub-interval has the length h, right? Now, if you do a further subdivision, suppose you get a new mess with the length of the sub-intervals as h by 2. Okay, you will be still able to reach the same accent, same point B, right? But a different h here, right? But in this, so what will happen to the error in this case? So you can say that, okay, here my error was ek, the global error was ek. So what do I expect here at this label? So you can see that it converges with the linear rate, right? So if you have you're reducing h by 2, your error will reduce only by the factor half. Okay, so this is one of the drawback of this method, that if you want to get a better and better accuracy, you can see you have to reduce h to be very small, right? You require h has to be a very small step size to get a good, or in a way to have a smaller error, right? So now we are going to see some methods which will have a better convergence than h, right? Say first we will see h square, and then we will see that can be even expect to get some higher order, say h raised to power k for any k. Okay, so this is what we are going to see further. So it turns out that if you look at this method, this Euler's method, so what is the formula we had to obtain the approximation at xk plus 1 is this, right? So you have the yk plus 1, which is the same as yk plus h times this term, which is a slope. Okay, so it turns out that in place of using this as a slope, if you use some average slope, okay, then you get a better approximation. So let's formally obtain the formula. So this is called the modified Euler's. So basically, we are going to modify Euler's method in certain way to get a better convergence. Okay, so let's see how do we do it. So what is the aim here? So the Euler's method can be modified to give second order of convergence. Okay, and let's see how do we modify it. So let's look back. What is the problem which we are finding the approximate solution of? So we have this problem, y prime is equal to f of xy. Okay, so here basically we are going to use that the equivalence which we have in terms of the integral equation, right? We saw that there's a relation between the solution of this differential equation and the integral equation. So basically it's based on that approach. So what do? We simply, and how do we obtain that integral equation? That is simply by integrating this differential equation, right? So that's what we are going to do. So we are simply going to integrate this differential equation. And what are going to be the limits of the integration? So we are going to integrate from xk to xk plus 1. And what we will get? So if we integrate the left hand side, so this will give us y at xk plus 1 minus y at xk. So I'm taking the y at xk to the right hand side. And then I will have the integration of this term. Okay. So one remark here before we proceed further. We can observe the Euler's method from this equation as well. So we used the Taylor's expansion to derive the Euler's method, right? Now, can you observe the Euler's method from this equation as well? What I should do? So what is the Euler's method? Euler's method is yk plus 1. This equals yk plus h times f of xk yk. Okay. So for this term, if I use the approximation, this is like you are applying the integration rules, right? So if I choose a suitable integration rule, I will be, you can observe that you get Euler's formula. So what is the integration rule I should expect here? So if you use this approximation, so basically you consider the approximation of the f by the constant. And what is that constant? You evaluate it at the first endpoint. Okay, so what you will get, the approximation of this term is going to be h times, because the length of this interval xk to xk plus 1 is h times f of xk y at xk, right? So if I try to obtain the formula, so what I will get, I'll get this formula using this relation, right? Because the approximation of this term is going to be h times f of xk yk, which we have in the formula here. Okay, so but what do we do in the modified version? So how do we modify it? So instead of approximating f by a constant, because when we approximate by a constant, we get the Euler's formula. So I'm going to use a trapezoidal rule. Trapezoidal rule meaning I'm going to approximate this function by a linear interpolating polynomial, right? Or directly I have a trapezoidal rule, right? So I can directly apply the trapezoidal rule for this term. So that's what I'm going to do. So we are going to use the trapezoidal rule. So now you can see that whatever the things you have learned before, like interpolation, you used it in the numerical integration, right? Now numerical integration, you are using it here in the differential equations. So this is, everything is interconnected, you know. You need, if you want to derive one thing, you need the information about the other thing. So then we use the trapezoidal rule to approximate the integral xk to xk plus 1 f of sys ds. Okay, so what we will get if we use the trapezoidal rule here? So we'll get y at xk plus 1. This, note that I won't be writing the equality here because I'm using the approximation by the trapezoidal rule, right? So I will write an approximation sign, which is going to be y at xk plus, so we will get, what is the trapezoidal rule? Can any of you recall? Suppose I want to integrate the function g on the interval AB. So what is the trapezoidal rule?
B minus A FA plus FB by 2.
Yeah, or either way, I can keep the 2 here. FA plus FB. That is the evaluation of the, sorry, G at A time plus G at B. So that is, if you evaluate the function at the endpoint, sum it up, and multiply by the length of the interval, divide by 2, right? So if we do the same thing here, what do we get? So we'll get, what is the length of the interval? Xk minus xk plus 1 minus xk. So this is going to be h by 2, and then evaluation of the function at the two endpoints. So endpoints is xk, y at xk plus f xk plus 1 y at xk plus 1. So this is an approximation. So if you want to write this as an equality, what you have to do? You have to add your error in the trapezoidal rule, right? You already have the formula for the error, which is, what is the error? So you check it out. I think it is going to be minus b minus a cube divided by
minus h square by.
Yeah, so I think this is cube divided by 12 into f double prime at some eta, where eta lies in the interval AB, right? You can just check it. I think this is the formula, we have it, right? So if you add this this error part here, then you will have the equality here, right? Then you know that your basically the exact value is nothing but the approximate value plus the error, right? So this error is nothing but IF minus I1F, if this is your I1F. Sorry, we are using G here, right? So the exact value is going to be this error plus the approximate value. So if you add this error term, you will have the equality here. So this also gives the idea that what is going to be the truncation error in this case, right? So first of all, let's write down what is a method, what is a modified Euler's method. So we are going to use this relation to obtain this modified Euler's method. So this is also called Euler's trapezoidal method, for the same reason that we are using the trapezoidal rule here. So the modified Euler's method is given by, so I'm going to use this relation. So I want the approximation of the y xk plus 1 is yk plus 1. This is going to be equal to yk plus h by 2 f at xk yk plus f at xk plus 1 yk plus 1. Okay, so you can write down the range for the k here. So this is the modified Euler's method. So let's give it equation number. Okay, but if you try to pay attention on this method, what you have got? So usually what you will be doing, so you have the y naught is given to you, right? So you start at x naught knowing the y naught, and then you compute the y1, then using y1 you compute the y2, like that, right? That's what we did an example for the Euler's method, and this is how this worked, right? But if you try to pay attention on this formula which we have got, so here you have to compute yk plus 1, right? Now yk plus 1, in the right hand side you have a yk, okay, this term also has xk yk, okay, but if you observe, this term also has the yk plus 1 sitting here, right? And f is a given function, it can be a linear, non-linear, whatever the function f is given to you, right? So you have to evaluate f at xk plus 1 yk plus 1 as well, and then you have to solve for this equation, right? So Euler's method, which we have seen before, it was explicitly giving you the yk plus 1 in terms of the yk. But here, this is an implicit relation, right? So you cannot directly compute yk, you can substitute here, but this is not a linear relation. F can be anything here. Okay, so because of this reason, this is also known as the implicit. This falls into the category of the implicit method, and in particular, it is called the Euler's implicit method. And the previous one, you can treat it as Euler's explicit method. Okay, so note that this relation this formula 5, this involves an implicit relation for yk plus 1. So thereby this is an implicit method. Okay, so if you have to refer it to the Euler's implicit method, so you call it as a Euler's implicit method. So in a way that if I say Euler's explicit method, it means that I'm referring to the one which we discussed before, right? And Euler's implicit method, meaning I'm referring to this one. All right. Now the question is that suppose you have to apply this method. So how will you solve? Suppose you have to, knowing yk, you have to find yk plus 1. So what do you have to do? How will you find it? You can just try to imagine with some simple expression of the f. Suppose f of xy is x squared plus y squared. So how you are going to solve for the yk plus 1 from equation number 5? So you have already learned the root finding techniques, right? You will be knowing the yk, xk plus 1. The unknown is yk plus 1 there. So you already know the root finding techniques to solve the nonlinear equations, right? So you are not, so until unless f is a linear function, you will not be able to directly find yk plus 1. So you have to apply the root finding techniques to find the yk plus 1. If f has some complex expression. Just a remark. So this formula 5, this is a nonlinear equation because it very well depends on the structure of the f and which can be nonlinear. And we are going to have, so this is a nonlinear equation, but what is the unknown? What is the variable which we want to solve for? It is yk plus 1. So with root yk plus 1, okay? So any root finding technique can be used to solve this equation, to solve for yk plus 1 using this formula. Okay. But then if you realize that this is a lot of the work, right? At each iteration, like knowing the y, say y naught, I'll be finding y1, and then for y1 I have to apply the root finding techniques, right? And then once I computed y1, I'll be finding about y2, and then again I have to apply the similar ideas, right? So if you have many steps to reach to the last step xn, then you are going to do a lot of it's going to be very much computational expensive, right? You have to do the two things. You have to apply the root finding techniques as well. So then there was a further modification suggested for this method that we can still have a method of order 2. Okay, let's talk about the order first before going to that. So what is going to be the order of the truncation error here in terms of h for this modified Euler's method? Any idea? Any guess? With some reasoning. So what is the truncation error for this method? So I'll look back to formula. So you just see this 5. So truncation error is going to be y at xk plus 1, right? And then I have the expression y at xk plus h by 2 f of xk y at xk plus f of xk plus 1 y at xk plus 1, right? Minus of this complete term. So this is going to be the truncation error, right? And what it is going to be, you can just, without doing all that Taylor's expansion and all, you can directly see how we derive this formula. So we use the approximation of this term, right? So whatever error is committed, it is committed by the approximation of this term, right? So here, as I said, if I want to write this equality, I can very well add this error term here. Error in trapezoidal rule. Right? So when you have the equality, this means that yk plus 1 minus yk minus h by 2 of this complete term, this is going to be just the error in the trapezoidal rule. Right? So this means the truncation error here, this is just the error which you will have in the trapezoidal rule. Okay? And you can see that is of order. What is the error? So this is going to be b minus a, that is the length of the interval where you're applying the trapezoidal rule. That is a whole cube, right? So the length of the interval is xk plus 1 minus xk, which is nothing but h. So it is going to be of order h cubed, right? So truncation error is going to be of this order. So I'm not going to explain how the global error is going to look like in this case, but the understanding remains the same, that if you try to simplify this, we will get this of order h square with the same reasoning that you will have h cube multiplied by n, and n times h is length of the interval. So this will give you h square. Okay. Let me write this as xn minus by n. All right. So it suffices to understand the truncation error, and using that, we can guess the global error. So you can see we got a higher order of the truncation error. So this is going to give you the better approximation than the Euler's method, the explicit Euler method. Okay, now coming back to that point that, that this is, as we saw, that this is an implicit relation, right? So you have to solve for yk plus 1 at each step, then you might have to apply the root finding techniques to find the yk plus 1. So with that reasoning, there was a further suggestion to modify this method, and again, to get a method with the same truncation error, that is, we don't want to lose the order of the truncation error. We still want to have the h cube as a truncation error, but modify this method so that we can get an explicit method. So that is due to the Huens. So this method is called the Huens method. So this is Huens method of order 2. Okay, because Huens has a other method as well. So that's why we refer it with the order here. Now, what is the modification? Like how do we really modify this method so that it also becomes explicit, and we still have the order of convergence for the truncation error as h cube. So the suggestion was that the problem is that yk plus 1 we are having here, right, in the argument with the f. So why don't we use a suitable approximation of this term again, so that we don't really require yk plus 1 to compute this approximation. We can use it with the previous data, that is knowing yk and xk, right? So the suggestion was that here in this place where we have yk plus 1 in the function f, inside the function f sitting, so I'll use the approximation of yk plus 1 by the Euler's method. That is, I have yk plus h times f of xk yk. So let me call this as yk plus 1 tilde. Okay, so you use this And then you compute the yk plus 1 as, so I'm using the same formula what we have in the this equation 5, yk plus h times h by 2 times f of xk yk plus f of xk plus 1 yk plus 1, right? I would have had this in case of the implicit Euler's method, right? But what I'm going to do, I'm going to modify this yk plus 1 tilde. Okay, because this was the problem creating term here. So I just used the explicit Euler's method to approximate this term as well. Okay, so basically what do we get? So that is, I have that yk plus 1, I'm going to compute it as yk plus h by 2 f of xk yk plus f of xk plus 1 yk plus h times f of xk yk. Okay, now you can see the right hand side completely depends on the known thing. That is, you have already computed yk, you know xk plus 1. So using that, you can compute the yk plus 1. All right. So let's give it a equation number. This is 6. And this method, this formula basically is known as the Hume's method. Hume's method of order 2. And for this method again, it can be checked that the truncation error is going to be of order h cube, right? So the global error is going to be of order h square. All right, and how will you find the truncation error? For this method, we just use this equation 6 and write down what the truncation error is going to be. And then you have to use the Taylor series expansion suitably. So you verify it. Okay, so we'll discuss this again in the next formula, the truncation error in a general case. So you can use the ideas from there in case you have some problem. But let's take one example to understand these this Hume's method. So example 1, so you have to determine the value of y at x is equal to 0.01. That will be too small. So 0.01, given that y at 0 equals 1, and the differential equation, associated differential equation is y prime is equal to x square plus y. Okay, and you have to use the Hume's method. Of order 2, whichever we just discussed. So what do we have? We have the point x naught as 0, right? And we have to reach up to 0.1, which is our xn in this case. And the given differential equation is y prime equals x squared plus y. So this is our fxy. Okay, so fxy here is x squared plus y. So what we have to find? We have to find basically y at this node. So let's see what h we should take. I mean, we can here, let me describe h also. So h, with the h you have to take it as, so let's try to reach it in 2 steps. So this is x1 and this is going to be x2. So h is going to be 0.05. Okay. So we have to go from x0 to x1, right? And then from x1 to x2. So first we have to find the approximation of y at the node x1, and then we have to use that to find the approximation of y at x2. So let's apply this. If you try to observe, Hume's method is telling that we have y1 is given by y0 plus h by 2 f of x0 y0 plus f of x1 y1, let's call it y1 tilde, where y1 tilde is y0 plus h times f of x0 y0. Right? So this is what we have from the Hume's method. So first let's find this and then substitute this to find y1. So what is y1 tilde? Y1 tilde is y0, which is given to be, so y0 we take it exactly, which is the same as y at 0. So y0 is y at 0, which is given to be 1. So this is 1 plus h by 2. So this is 0. Okay, we are computing y1 tilde. So h is 0.05 and f is x square plus 5. So this is going to be x0 square plus y0. Okay, so x0 square is 0 and y0 square is 1. So let me write directly the numbers here. So you're going to have it 0 plus 1. Okay, so upon simplification, you get this. Now we have y1 tilde, so we can find y1. So y1 is going to be y0. So y0 is 1 plus h by 2, 0.05 by 2, f of x0 y0. So this is going to be x0 square plus y0. And then this is going to be x1 square plus y1 tilde. So this is 0. And this is x1 is 0.0. What is x1? 0.05 square. Y0 is 1. And y1 we have just computed 1.05. Right? So if you simplify this, let me see what do I get. So I get this as 1.0513. Okay, so you can verify this calculation. So now I have found y1, but what is our interest? We want to find the approximation of the y at 0.1. So I'm going to compute y2 using y1. Again, using the Hume's method. So y2 is going to be y1 plus h by 2 f of x1 y1 plus f of x2 y2 tilde, and y2 tilde I'm going to compute it using the Euler's method, which is y1 plus h times f of x1 y1. Okay, so we just have to substitute the data here because we already know y1, right? So we can find y2 tilde, which is y1 plus h is 0.05 times x1 square plus y1. So you substitute here, x1 is 0.05 and y1 is 1.0513. So if you simplify this, we get it as 1.1040. Okay, you can take the help of the calculator to do these computations. So once we have this, now we can find y2, which is y1. So y1 is 1.0513 plus h by 2 f of x1 y1. So x1 square. So x1 square is 0.05 square plus y1 plus x2 square. So x2 is 0.1 plus y2 tilde. Y2 tilde is 1.1040. Okay, and you can just verify this calculation that I think we get it as we check 1.1055. Okay, and you can try to find the exact solution of this problem and see whether you're able to match it with what you're getting the approximate value from using this method. Okay, so this is how this method works. Any doubts so far? Okay, if not, now what we have done, we obtained a method which converges with the order h, then we improved it to get order h square. Now we can ask this question further, that can we get a higher order convergence as well? Like why h square, why to stop at h square? Can we expect a, so if everything is nice, can we get h, design a method which will converge with order h raised to power p in general, right? So basically we are interested in, okay, let me give a little motivation. So note that if you want to design a higher order method, you can say that, okay, I have a Taylor series expansion. So say, for example, you used it in the deriving the Euler's formula that y at xk plus 1, which is y at xk plus h times y prime at xk plus h square by 2 y double prime at xk, and likewise, right? So you say that, okay, I do not truncate it as a at the second after the h square, I truncate it, say h raised to power after the h raised to power n. So we have h raised to power n plus 1 divided by factorial n plus 1 into yn plus 1 evaluated at some jk, right? Where jk lies between xk plus 1 and xk. Right. So you can say that suitably I can design a method rather than truncating it like in the Euler's method we truncate it here. So rather than that, I can truncate it say at this point. So I will have a truncation error is of order h raised to power n plus 1. Right. And here these note that if you want, you are given the information that y prime is f of xy. Right. So you can observe that to compute y double prime, you have to differentiate this equation. So y double prime is going to be, so f is a function of x and y both. So I have to use a chain rule here. So this will be the derivative with respect to x, and then the derivative of x with respect to x is going to be 1. And then I have a derivative with respect to y, and the derivative of y with respect to x is going to be y prime, and y prime is f again. Okay. Is it okay? So I've simply applied the chain rule here. Likewise, if you find the higher order derivatives, so you can see that you will require to compute the derivatives of the f as well. Right? So if you want to have all these terms in your method and so that you truncate it at this level, so you have to compute all these derivatives, and they are going to involve the higher the order you want here, they will involve that many derivatives of the function f as well. Right? So we don't want that, right? We don't want to impose additional conditions on the function f that it has to have that many derivatives, etc. So then there's another class of methods which does not require the computation of the higher order derivatives, but it still give you the desired convergence. That is, we are expecting a convergence of say h raised to power p. We can still design a method having the error of this order, but without computing the derivatives of the f. Let's see how do we do that. So this class of method is called the Dorangi-Kutta methods. So you are going to see that it is not just one method, it is a class of the method that we are going to get So we'll start with a simple case and then see what happens for the higher cases. So let's first understand the simplest case, which is so I'm going to refer it as RK methods, okay? Rather than writing the complete term, I'll call it as RK method. So the first method here is the RK method of order 2. Okay, so we understand this method in detail, and then we'll just try to generalize it for the any P. Okay, so again, the underlying idea remains the same, that we want to compute yk plus 1. That is, we will be having the method of this form. So you can see here, this method or the previous method as well. So we have yk plus 1, which is given by yk plus some h times. This is average slope, right? This is 1 by 2 of this is nothing. This term is nothing but this f is denoting the slope here, right? So this is in a way, this is average slope here, right? So we will have a similar form here as well in this method as well. So let's write it down. So what is the general form of this method? Not just this method, all the methods will have this form, all the RK methods which we will discuss. So the general form of all the RK methods is given by, so we want to find yk plus 1, and this will be given by yk plus h times. You will have some slope in terms of the f, right? So let me denote that average slope by capital F here. So the slope will be at the point xk, yk. Okay, and as a function, if I write, this function might depend. Okay, so if you want to see what all variables it will depend on, because I'm writing it as a new function, so it will depend on, other than the xk, yk, it will depend on h and f. Okay, so basically here, this quantity, this basically this function, so this can be thought of as an average slope of the solution on the interval xk plus 1. Right? That is, if you try to relate it to the previous method, so this f of xy, let me skip writing f every time because it's understood that it will, I'm talking about the average slope, so it will depend on f as well, because I have to again and again write this f expression. So let me just write with the h. So this is basically going to be approximation of the y prime of x, which is nothing but f of x by x. Right? For example, in the case of the Euler's method, this f was simply evaluation of the small f at xk, yk. Right? So for example, for Euler's method, this f would be simply f of xy. Right? Likewise, you can see what it will be for the modified Euler's method. But here in this RK method, what is going to be this average slope? So let's write it down. So for this method, and specifically when we are considering the method of order 2, so we suppose that f is this form. So suppose f equals, let me write, suppose f has the form. So here again, if you try to see in the modified Euler's method, right? So we had an average slope, but you can see that average was just between 2 points, right? And we took the coefficients as 1 by 2 times f of xk yk plus 1 by 2 times this term, right? So here we are going to take a general constants. So I'm going to have it as, say, gamma 1 times f of xy plus gamma 2 times f of x plus alpha h y plus beta h f. So it's a similar way what we have in the Hume's method, right? If you try to see on the Hume's method, we have f of xk yk plus f of xk plus 1 yk plus h times f of xk yk. So in particular, I'm just taking a general constants here. Instead of the 1 by 2, I'm taking gamma 1, right? And instead of the 1 by 2, again, I'm here having the multiples of gamma 1 and gamma 2 here. And alpha was 1 in the case of the Hume's method, and beta was also 1. Okay, so I've just taken a general form of what we have in the Hume's method case. All right, and here these gamma 1, gamma 2, alpha and beta, these are unknowns. So, and these unknowns we have to determine in some way, right? So where we determine, okay, so let me write that. So these gamma 1, gamma 2, alpha and beta, they are unknown constants. At this point, they are unknown, and we are going to determine them, which are to be determined such that what is the expectation? How we have to find this method so that the truncation error is of order h raised to power 3. Right? So we are going to determine these constants such that the truncation error will be of order h cube. Okay, so is the problem clear with what we are trying to do here? Any doubts so far? Okay, so now you have to tell me what is the truncation error in this method. I've already given you the method, right? So what is going to be the truncation error in this method? Anybody? So method is in front of you. What is the truncation error? I have to just see that this is the method. What happens when I try to test it with the exact solution, right? So that is I'm going to consider. So what is the truncation error? Let's call it tk plus 1. So it is going to be y at xk plus 1 minus. So I will have the term corresponding to this, right? So y at xk plus h times f of xk y at xk and h. Is it okay? Okay, so let's give them the equation numbers. So 6, 7, 8. And this is going to be 9. Okay, so now what we have to do, we just have to simplify this truncation error, right? Because this is the place where I will get some conditions so that I can determine these unknown coefficients, gamma 1, gamma 2, alpha and beta. So we just have to simplify this truncation error. And we know how to simplify it. We have already done it before. Say for the explicit Euler's method, we have to use a Taylor's expansion. So we use Taylor's theorem to simplify the truncation error. So let's start. So let's look at this term first. Okay, so y at xk is okay. There's nothing I can do here. In the second term, I have to see what is capital F. Capital F is given by this 8, right? So let's write it down. That capital F is, this is gamma 1 times f of xy plus gamma 2 times f of x plus alpha h y plus beta h f of xy, right? So if you substitute xk yk here, so you will get f of xk yk plus this term also evaluated at x is equal to xk, y is equal to yk. Okay, so substituting xk yk is not a problem because I need here f of xk y at xkh. Okay, so in place of x, you can take here xk and y is going to be y at xk. All right. So if I want to apply Taylor's expansion, you can see that there's nothing I can do in this term, right? Because this is going to be f evaluated at xk and comma y at xk, right? So the Taylor's expansion I can apply in this term. Okay, so what do I have? So we are going to use the Taylor's theorem in 2 variables because you can see that I have x plus alpha h and y plus something, right? So you have f is a function of x and y both. So you have to apply Taylor's theorem in 2 variables. So in case you do not recall what is the Taylor's theorems for the multivariable case, I just ask you to please go and check it. Okay, so I'm just needing it here for 2 variables. So it is going to be, so what we have, x plus alpha h, y plus beta h, f. Okay, so you can treat this as say x plus, say we have not used the coefficients a, so, or let's call it say x plus gamma 1 is already used. So say x plus delta 1 and y plus delta 2. So what is going to be the expansion? So I'm going to expand it in the neighborhood of x comma y. So we'll get it as f of x comma y plus what I'm going to get. So the first term will be, so the difference of x and x plus alpha h. So this is going to be alpha h, and the partial derivative of f with respect to the x, right? And this will also be evaluated at xy. Okay, so everything is evaluated at xy here. And then I will get the difference of y plus with y plus delta 2, which is delta 2. So delta 2 is beta h into f. So I'm not writing xy again and again because it's understood that we are expanding in the neighborhood of xy. So let me write here itself. So beta h f. This is the difference of y plus delta 2 with the y, and then the derivative of f with respect to the second variable, which is y. Okay, now you have to tell me where I have to stop in this truncation, in this expansion. Can you tell me? Seeing that what we are wanting, we want that our truncation error should be of order h cube. It is like predefined thing now that I just want the error to be of h cube. So can you tell me that till what point I should expand this Taylor series? See, you have already have written formula here in the equation number 9, right? So if you try to see this expression f, this is coming into this expression here, right? And you have already multiplied by h factor. You have h sitting there. So if you want the truncation errors of order h cube, so it suffices to have the truncation error in this function of order h square, because h you are multiplying here. Right? So I can very well stop here. I don't have to go to the next term because here my truncation errors in the next term, the next term is going to be of order h square. Okay, and h is sitting here. So I will get basically when you will substitute here, you will get it of order h cube. So this term will become order h cube. Okay, so I can just keep at this point. I can stop it at this point itself because this is what I desired. So then we have the expansion of this term. Therefore, okay, let me write this in case it is confusing, that all the evaluations here are at xy, where all the functions are evaluated at xy in the right hand side. Okay, therefore, I'm just going to substitute this in this f. So capital F is going to be gamma 1 times fxy plus gamma 2 times, so I'm substituting this expansion here. So this is f of fxy plus alpha h fx plus beta h f fy, and then order h square I can keep it separate because this will be getting multiplied with the gamma 2, but gamma 2 is a constant again, right? So it just gets combined with this order. All right. So let me just take out h from here. So we have gamma 1 times this plus gamma 2 times f of xy plus h, I can take it out. So this is going to be alpha fx plus beta f into fy plus order h square. So far we have order h square only, but when we will substitute in the truncation error, it will become order h cube. Okay, what else we have in the truncation error? So this term is okay now because if you observe, I got everything in terms of the xy. Okay, and when you will substitute x is equal to xk and y is equal to y at xk, everything will be in terms of the xk and y at xk. So this is okay. Now, only thing where I can expand further is the first term, right? So y at xk plus 1. So further, y at xk plus 1 is going to be y at xk plus h, right? And I can use the Taylor's expansion here. So we have that y at x plus h, this is going to be y. So I'm expanding in the neighborhood of x. Okay, so y at x plus h times y prime at x. Now, can you tell me where I should stop for this term?
H cube.
Yeah, so you can see here that for this term, since you're demanding the error to be of h cube, you have to go up to the, you have to stop it at the h cube itself, because you don't have this case here that you have some h multiple here. Okay, so I have to get one more term here. So this is going to be h squared by factorial 2 y double prime plus, and then you will have h cube term. So I don't have to write the further terms. Okay, so first term is okay. Second term, y prime, we already know that y prime is f of xy, right? So this is hf evaluated at x comma y. So let me again skip writing everything, evaluations. So then h square by 2, and what is going to be double prime of y? We have already done before. So this is going to be using the chain rule. So this is fx plus fy, and then the derivative of y with respect to x, that is d by y dx, which is f again. Okay, so this is fx plus f into fy plus order h cube. Okay. And again, all the evaluations here, the same thing, what we have written here. So all the functions are evaluated at. All right, so now we have everything. So we can just simplify the truncation error. So tk plus 1, which is yk plus 1. Sorry, what I wrote here. Yeah, this is correct. Y at xk plus 1. Y at xk plus 1 minus y at xk plus h times f of xk comma y at xk, right? So let me simply take this term y. So this is like xk plus h, right? So let me take x plus h. So in place of writing xk every time, I just want to keep everything in terms of x, and then I'll substitute x is equal to xk, just so that I get some extra space to write the steps here. So minus yx plus h times f of xk, sorry, x yx h. So let's simplify this term, because when we will take x is equal to xk, we will get the truncation error. So this is going to be, we have already got the expansion here. So this is y plus hf plus h square by 2 fx plus fy plus order h cube, right? So this is the expansion of this term minus y and then plus h times of this term. So we have it gamma 1 f plus gamma 2 f plus h times of this, f plus alpha h fx plus beta hf fy, this complete thing. And then for this term also I'll get order. So let me just combine this here and let me write order h cube. Okay, so now let's club terms together. So y cancels out. And what I have, I'm just combining all the terms with the h square, likewise. Okay, so as a multiple of h, I have f from here, sorry, f, and then gamma 1f, and then gamma 2f. So I will get 1 minus gamma 1 minus gamma 2 times f. And let's combine all the term with the h square. So note that fx plus, okay. So what I get as a multiple of h square. So let's see with respect to the fx. So I will get 1 from here, right? I'm seeing as a multiple of fx. So I'll get 1, and then I'll get from this term. So this is going to be minus 2
alpha.
Gamma 2, right? And now let's combine the term with the f into fy. So this is going to be from here I have 1, and then from here I will get beta times 2 gamma 2. So this will be minus 2 beta gamma 2. Okay, and then order h cube. Okay, so thereby the truncation error tk plus 1, this is going to be the same expression, but everything will be evaluated at xk, yk. So this is going to be h times 1 minus gamma 1 minus gamma 2, f plus h square by 2, fx 1 minus 2 alpha gamma 2 plus f into fy 1 minus 2 beta gamma 2 plus order h cube, where all the functions are evaluated as at xk, y at xk. Okay, so they have same arguments for all the functions. Now, what do we desire? We desire that the truncation error has to be of order h cube. Right? So what we will require for this, that the coefficient of h and h squared, they has to be 0. Right? So which require the coefficients of h and h square to be 0. Right? So what does this imply? That if we want the coefficient of h to be 0, this will imply that 1 minus gamma 1 minus gamma 2, this is equal to 0. That is, I get the first equation, that gamma 1 plus gamma 2 has to be 1. And then I have 1 minus 2 alpha gamma 2, this is equal to 0. Right? So this is the second equation I get. That 2 alpha gamma 2, this equals 1. And the third equation we get it as 1 minus 2 beta gamma 2, this also equals 0. That is 2 beta gamma 2, this is also equal to 1. Okay. So if we assume that gamma 2 is not equal to 0, then we can get all the other variables in terms of gamma 2. So then alpha is going to be 1 by 2 gamma 2, beta is going to be 1 by 2 gamma 2, and gamma 1 is going to be 1 minus gamma 2. Right? Where gamma 2 is arbitrary. Okay, so thus For each value, non-zero value of the gamma 2, you get one method, right? Because once you fix gamma 2, you can determine your alpha, beta, and gamma 1. And for the values of these four constants, you get one method. Okay, so basically we have not just got one method, we have got a class of the methods, right? So thus there is a family of Runge-Kutta methods of order 2 depending on the choice of gamma 2. Okay, now let's try to take some choices of the gamma 2 and see what happens. So let's take gamma 2 equals to 1 by 2. So what do we obtain in this case? So we will obtain, so let's substitute if gamma 2 is equal to 1 by 2, gamma 1 is also going to be 1 by 2, alpha is going to be 1, and beta is going to be 1. So what is the method we have obtained? So yk plus 1, this is going to be yk plus h times. You have gamma 1 times f, right? So gamma 1 is 1 by 2. So let me keep the factor 1 by 2 outside. F at xk yk plus gamma 2 is also 1 by 2. So 1 by 2 factor is outside. And then f at x plus alpha h. Alpha is 1, beta is 1. So we will get xk plus h and yk plus beta h. Right? And I think you already identified this method, isn't it? So this is the same as the Yoon's method of order 2. Right? But we can write this in this compact form. So I can write this as yk plus 1 as yk plus 1 by 2 k1 plus k2, where I'm defining k1 as, so it is going to be the h times f of xk yk, right? And k2 is going to be h times of f of xk plus 1 yk plus, so you can observe you will get this term which is nothing but k1. Sorry, beta is 1 here. Yk plus k1. So that is, once you have computed k1, you can use that information to compute the k2, and then once you have k1 and k2, you can use that to compute yk plus 1. All right. So eventually, the way we have find these coefficients, you can see that the truncation error is of order h cube, so the method is going to be of order h square. All right, and you can, one more thing you can observe, that when you take gamma is equal to 1 by 2, you get the Yoon's method of order 2. Right? Now let's take one more choice of the gamma 2. So let's take gamma 2 equal to 1. So if we take gamma 2 is equal to 1, what is the method we are going to get? So note that gamma 2 is 1, so gamma 1 will be 0. Okay, so for this choice, gamma 1 will be 0, alpha is going to be 1 by 2, and beta is also going to be 1 by 2. So we will have the method as yk plus, so only one term will be here, h times f of xk plus alpha h. Alpha is 1 by 2, so we get h by 2. And then yk plus beta, so beta is also 1 by 2. So h f of xk yk, h by 2 here. Okay. So this is, if you try to observe, what is this method? So you have the interval xk and xk plus 1, right? So you're basically how will you get this method if you just try to think? So with the same analogy as we have Euler's method. So basically we have this integral xk to xk plus 1 f of s ys ds, which we have used the approximation by the trapezoidal rule to get the modified Eulers, right? Or you use the approximation by the constant to get the Eulers. So likewise, if you use the approximation of f by the midpoint, the evaluation of the f at the midpoint, that is f is approximated. So if I write it for any function g, suppose you approximate the g by the evaluation of the g at xk plus 1 by 2, that is a midpoint, right? So you will get the approximation of this term as length of the interval h times the evaluation at the midpoint, right? Which is what this method is. If you try to observe, this is the same method you get. So with that reason, this is known as the midpoint method. Okay, so you please try to observe this thing. That, of course, we can name it, this is a sum method, but why we are calling it as a midpoint method, you can just see that if you use the midpoint rule to approximate this integral, you will get the same method. Okay, that's the reason we are calling it as a midpoint method. Okay, I think it's the time. So if you have any questions, we have 2 minutes. Otherwise, I'll stop here. Any questions? All right, if not, then we end this meeting here. Thank you.
Thank you, ma'am.